Okay, so in this video we want to look at finding the area between two curves. Now technically this isn't part of the Unit 1 and 2 syllabus, we don't cover it in Year 11, but I think it follows really naturally from finding the area under a curve. I also think it gives you an alternative method for finding area under a curve, or an alternative way of understanding it. And I also know that it's something that my Year 12 students make really hard work of when it's really not that difficult. And so I think if we can introduce it now and then allow you to see it for a second time in Year 12, hopefully you'll be able to do it better when you get to Year 12. As I said, I find the students in Year 12 often use far too many integrals for very simple areas because they're not thinking clearly about what's happening. Okay, so we can use definite integrals to calculate the area between two curves. So I want to have a look at the three different cases, because in the previous video we looked at the fact that if the region is below, when we're finding area between the x-axis and the curve, if the region is below the x-axis we need to use a negatively signed integral, or we need to reverse the limits of integration. So what I want to look at here is I want to look at, okay, what happens if I'm trying to find an area between two curves. As you can see, I've got highlighted in green there, an area between the red curve and the blue curve, between x equals a and x equals b. But what would happen if both of those curves were below the x-axis, and what would happen if one of those curves was above the x-axis and one was below the x-axis? So I want to investigate these three situations, but I want to investigate these three situations independently to actually show you that it doesn't matter where the x-axis lies. Okay, I'm not trying to make things more difficult here. Hopefully I'm going to illustrate to you that you get the same thing every time, and so therefore you don't need to worry about where the x-axis lies when you're finding an area between two curves. So let's work through the algebra that verifies that. So if we wanted to find this green area in here, the best way for us to do that would be to find this red area there, and then take away this blue area down here. Okay, so if we could find the total red area and then subtract the blue area, that would give us the green area. Okay, so we know that the red area, so the green area is going to be equal to the red area, which is the integral from a to b of f of x with respect to x, minus the blue area, which is the integral from a to b of f of x. Now, because these two integrals have the same limits, we're integrating, doing both, sorry, not f of x, the blue one, it's g of x for the blue one. So because both of those integrals have the same limits, we can actually write those together. That's actually just the one integral. Okay, so that is the integral from a to b of f of x take away g of x. So we wouldn't calculate it as two separate integrals. This is one place where you'll calculate more integrals than you need to. You wouldn't do this, okay? You recognize that that's the same as this, and you evaluate one integral. Alright, so if they're both above the x-axis, it'll be the integral from a to b of f of x minus g of x. Alright, let's have a look at the second one. So here, to find this area. So we want to find the green area. So to do that, we're going to need to find this blue area here, and then take away this red area. Okay, so the blue area, it's an area under the curve, so it's a negative integral. I'm going to write it as a negative integral here, from a to b of g of x. That's the blue area. And then we would want to take away the red area, which is a negative integral, again, because it's under the x-axis, from a to b of f of x. Okay, so let's be clear about what we've got here. So this is the negative integral from a to b of g of x plus the integral from a to b of f of x, which is the same as the integral from a to b of f of x take away the integral from a to b of g of x, which, given that the limits on those integrals are the same, is just the one integral from a to b of f of x take away g of x, which is the same as what we got when both curves were above the x-axis. So you'll notice in all three examples, f of x represents the top curve and g of x represents the bottom curve. Okay, so it is the integral of the top curve minus the bottom curve. When they're both above the x-axis, when they're both below the x-axis, it is also the integral of the top curve minus the bottom curve. Okay, let's have a look at what happens when one is on either side of the x-axis. When both are on either side of the x-axis. So the best way for us to find the green area here would be to find that red area, which is the area between f of x and the x-axis, and add it together with that blue area, which is the area between g of x and the x-axis. Okay, so our green area here is going to be equal to the red area, which is the integral from a to b of f of x, so it's above the x-axis, that's a positive integral. And then in this case we want to add that together with the blue area, which is a negative integral from a to b of g of x. Okay, so that is the integral from a to b of f of x plus minus, dx, plus minus, so minus the integral from a to b of g of x. And once again, we've got integrals with the same limits, and so we can combine those together into the one integral. That is the integral from a to b of f of x, take away g of x with respect to x. So once again, this is the top function minus the bottom function. And what we see here, let me just zoom out for a minute so you can see them all at once, is that all three, whether both curves are above the x-axis, whether both curves are below the x-axis, or whether one is above and one is below, it is the same thing every time. So the point that I'm trying to make here is that you don't need to treat them differently. It doesn't matter where the x-axis is, the area between the two curves will always be the integral of the top minus the bottom. And you do it as one single integral. Yes, you can get to the same answer by integrating them separately, but you end up doing twice as many substitutions. You've got more subtractions, more potential to lose track of negatives, you're subtracting negatives, and much more potential to make mistakes. So the area between two curves is the integral of the top curve minus the bottom curve. Okay, so regardless, always. All right, let me just zoom that back again. Okay, so as I said, in general, the area of the region bounded by two curves and the lines x equals a and x equals b is the integral from a to b of the top function minus the bottom function. And this rule applies no matter where the x-axis lies in relation to the curves. Okay? So the only thing we need to worry about, the only time we would need separate integrals is if what is the top and what is the bottom changes. So for example, in this question here, from a to b, f of x is the top curve and g of x is the bottom curve, but from b to c, g is the top and f is the bottom. So in that case, we would need two separate integrals because what is top and what is bottom changes. So this shaded area would be the integral from a to b of the top function, which is from a to b, it's f of x, minus the bottom function, which is g of x, dx, so that's that bit, plus it would be the integral from b to c of the top curve, which is g of x, minus the bottom curve, which is f of x. And that's going to be that bit there. So you would need two separate integrals if the top and the bottom curves change. One thing I want to be clear about is, and one of the reasons I think this is important when you do know how to do area under the curve, is if you think about, let's say we've got y equals f of x, and we're trying to find this region here from x equals a to x equals b, versus if it was this one, y equals f of x, and you're trying to find this region here from x equals a to x equals b. Okay, so we already know that this would be a positive integral. The top one would be a positive integral, so maybe the red one would be a positive integral and the blue one would be a negative integral. We already know that. But one way you can think about this is you can always think of areas as being between two curves. Okay, so in this case, the top curve would be y equals f of x, and the bottom curve is the x-axis, which is the line y equals 0. So if you always think about it as being an area between two curves, it is the integral from a to b of the top curve, which is f of x, minus the bottom curve, which is 0 with respect to x. And so it's just the integral from a to b of f of x with respect to x. If we think about this, the top curve here is the x-axis, which is y equals 0. The bottom curve here is y equals f of x. And so this is the integral from a to b of the top curve, which is 0, minus the bottom curve, which is f of x. And so that is the integral from a to b of negative f of x. which is the same as it being the negative integral from a to b of f of x, or the same as b to a of f of x. So if it helps, you can just always focus on this being how we find areas, understanding that the x-axis is the line y equals 0. So you can use that as your top or your bottom function as relevant. And that can help you to avoid having to think about, well, is it negative or is it positive? You still need a graph. You still need to be able to see what's the top and what's the bottom. It doesn't avoid you drawing graphs, but it might be another way to think about it. And the point is that it doesn't contradict what we already understand about the negative areas. We do see if the graph is below the x-axis, the top curve is y equals 0, and so we get the negative from subtracting the bottom curve. Okay. All right, let's do some examples here of areas between two curves. Again, the first thing has got to be, you have to draw it and see what you're dealing with. Find the area bounded by the curves y equals x squared, the line y equals x between x equals 0 and x equals 1. Okay, so y equals x squared is a parabola. Y equals x is a straight line. And they do intersect when x equals 1. They both go through the point 1, 1. And they intersect at the origin. Okay, and so therefore, if we want to find the area bounded by the curve, the line y equals x, and the lines x equals 0 and x equals 1, it actually doesn't even need to say that, because the area bounded between the parabola and the line is the area between x equals 0 and x equals 1. Okay. Alright, so we're finding that region in there. So we don't need to calculate any points of intersection. We can do that. I mean, you can if you want. You know, solving x squared equal to x is x squared minus x equals 0, which is x minus 1 equals 0. And so x equals 0 or 1. That confirms that they intersect when x equals 0 and 1. But these are simple enough functions that you should be able to work that out. Okay, so the area is going to be the integral from 0 to 1 of the top function, which is x, minus the bottom function, which is x squared. And then we just work that out. Antiderivative of x is x squared on 2, minus antiderivative of x squared is x cubed on 3, from 0 to 1. Okay, so when we sub in 1, we get 1/2 minus 1/3. Take away, subbing in 0, we get 0 minus 0. So it's just half minus a third. Half is 3/6 minus a third, which is 2/6, and so that area is 1/6 of a square unit. Okay, example 2. Find the area bounded by the curve, bounded by the curves, I should say, y equals x squared and y equals 8 minus x squared. Okay, so y equals x squared is the parabola. Y equals 8 minus x squared is the reflected parabola up by 8. So it's going to have the same shape, but it's going to go that way instead. So that would be at 0, 8 up there. Okay, so we want to find the area of the region bounded by these two curves. So that's going to be this region in here. So we need to know what the limits of integration are, which means we need to know what these 2x values are. So we need to actually find those first. So quite often you'll need to find points of intersection before you can go on to find your area. Okay, so for the points of intersection, it's going to be x squared equals 8 minus x squared. Adding x squared to both sides, we get 2x squared equals 8. Dividing both sides by 2, x squared equals 4. And so x is plus or minus square root 4, which is plus or minus 2. Okay, so this is minus 2 and this is positive 2. Now the other thing I'm probably going to note here is that I've got some symmetry happening here. So I could instead just find this green area and double it. Alright, so we can either say that our area is going to be the integral from negative 2 to 2 of the top curve, which is 8 minus x squared, take away the bottom curve, which is x squared. Or we could do 2 times the integral from 0 to 2 of the top curve, which is 8 minus x squared, minus the bottom curve, which is x squared. Now, before you do your antiderivative, if you can collect some like terms from having subtracted the functions, we want to do that. So 2 times the integral from 0 to 2 of 8 minus 2x squared, and now we'll antidifferentiate. So that's going to be 8x minus 2x cubed on 3, from 0 to 2. Okay, so we have 2 times, subbing in 2 gives us 16, minus, now 2 cubed is 8, 2 times 8 is, that's 16 on 3, and then we want to take away, that'll be 0. Alright, so we're going to have two lots of 16 minus 16 on 3. 3 16s are 48. So it's 48 on 3 minus 16 on 3. So it is 2 times 32 on 3, which gives us 64 on 3 square units. So the green area is 32 on 3, therefore the red area is 64 on 3. Okay, and then I think our final example here. Calculate the area bounded by x cubed minus 3x and y equals x. Okay, so x cubed minus 3x, x is a common factor there, leaves us with x squared minus 3. So the x-intercepts are going to be at 0 and plus minus root 3. It's a positive cubic. So it's going to look something like that. That's positive root 3. That's negative root 3. And then we also want y equals x, which is going to be something like that. Okay, so the area bounded by, so we've got two regions, that bit over there and that bit over there. Okay, yes, it crosses over the x-axis, but that doesn't matter. And again, I'm going to note the symmetry. So the fact that these two x-intercepts are symmetrically about the y-axis and it goes through the origin means that the cubic has some symmetry, as does the line. Okay, it's got actually rotational symmetry. If you were to rotate that 180 degrees, you get the same thing. And so therefore those two lumps, those two shaded regions are actually equivalent. So I'm going to find this area by, again, doubling one integral. Okay, so we could either do it, actually before we can find the area, we need to know these x values where they intersect. So we need to know those points. So we want to solve them equal to each other. So we're going to have x cubed minus 3x equals x. So that is x cubed minus 4x equals 0. So that is x times x squared minus 4 equals 0, which is x times x minus 2x plus 2, difference of two squares, and so x equals 0 or plus minus 2. Okay, so this is 2 and this is minus 2. So we could find the area by doing the integral from negative 2 to 0 of the top function, which would be x cubed minus 3x, take away the bottom function, plus then the integral from 0 to 2 of the top function, which is x, take away. Now be careful when you're subtracting this bottom function because it's got more than one term, so you need brackets there so that you do end up with the minus minus. Okay, so we could do it that way, or actually because we recognise that those are both the same, we can just do two lots of one of those integrals, and I'd prefer to substitute in the positive numbers. So I'm going to do two lots of the right hand side. Again, be careful about subtracting the functions. If your second function has more than one term, you're subtracting the whole of the second function. Okay, so again, let's tidy that up before we anti-differentiate it. So 0 to 2, it's x minus x cubed plus 3x. So it is the integral from 0 to 2 of 4x minus x cubed. Okay, again, I've left us not a lot of space. So antiderivative, so it's going to be, so we can have two lots of the antiderivative. Antiderivative of 4x is 4x squared on 2, so that's x squared, 2x squared. And then it's minus x to the 4 on 4, and we are doing that from 0 to 2. Okay, so it is 2 times, subbing in 2. 2 times 2 squared is 2 times 4, so that's 8. Take away 2 to the power of 4 is 16, on 4 is 4. And then minus, subbing in 0. Again, just be careful about omitting that 0 step. You'll make mistakes in Year 12 when they're exponentials and trig functions and subbing in 0 doesn't give you 0. Alright, so it's 2 times 8 minus 4, so it's just 2 times 4, and so it is 8 square units. So each of those red lumps is 4 square units, and so the total shaded area is 8 square units. Okay, the work today is from a worksheet finding the area between two curves, so making sure you do your sketch first, you find any coordinates of any points of intersection that are going to be needed in the integration, and then you set up the integral bearing in mind that you don't need to worry about where the x-axis is, it is just the integral of the top function minus the bottom function.